So we are looking at chapter 14, the first of 3 chapters dealing with equilibrium. This is kind of the general overview of equilibrium. This is a really key chapter to understand because equilibrium is a huge piece in AP chemistry, and it's the foundation for the following chapters. So super, super critical. Now, a few things I want you to remember about equilibrium as we deal with it. 1, if we say that something has reached equilibrium, that means that the concentrations of our reactants and products are no longer changing with time. That's how we know that something has reached equilibrium. In prior chemistry, we'd almost pretend that the reaction had stopped at that point. But it hasn't. It's still going. It's just not giving a net change anymore. To have equilibrium occur, neither the reactants nor products can actually escape from the system as a whole. They need to be contained. And finally, at equilibrium, there is a particular ratio of the reactants to products concentrations that equals some constant, and that's going to be critical. So we're going to start with 14.2, just the delving into equilibrium. So in equilibrium, we're dealing with what is called a reversible reaction. And that means that both the forward and reverse reactions are taking place at the same time, at the same rate. And we call that point at that juncture a dynamic equilibrium. It's called dynamic because it's still technically changing. The forward and reverse reactions are still occurring, but it's an equilibrium because they've reached a balance and there's no net change. So here's kind of an analogy. So we have two countries, country A and country B. We can see initially there's a net movement from A to B. But over time, as B's population grows, people then start to migrate from B to A, and eventually an equilibrium is reached where the rate of people transferring from one country to another becomes the same. It doesn't mean the concentrations or the populations are the same. It just means that they become steady. Okay, 14.3. So that was a very short section. The equilibrium constant, capital K. Again, chemists are not good at spelling, so we keep using K's for constant. Again, this is an uppercase K, not a lowercase k. Lowercase k's, again, are rate constants. This is the equilibrium constant, which is an uppercase K. So, anytime we have reversible reactions, this will inevitably lead to an equilibrium. Regardless of how complicated the reaction is, regardless of the kinetics, regardless of how many steps it is, if you have a reversible reaction, equilibrium will occur. And that means that we can approach equilibrium either by starting with the reactants or by starting with the products. So there's something called the law of mass action. You'll never hear this again, but the idea is sound, that for any reaction, the relationship between the concentration and reactants, the concentration of the reactants and the products can be expressed by a constant. And it's the ratio of the products to reactants at equilibrium. And that, at its heart, is the equilibrium constant. So, when we talk equilibrium constant, there's the equilibrium constant, which is a number, and the equilibrium constant expression, which is a formula. So here is a general equilibrium equation. The uppercase letters would be chemical formulas. Lowercase would be their coefficients. And you might wonder, Ms. Anderson, where's the C? Well, obviously, you're in Iowa where you don't see it. Okay, that was a terrible joke. Anyway, if that is our general equation, the equilibrium constant expression is expressed by this. The lowercase c there is telling us that we're using concentration. That's what those hard brackets there are indicating, concentration and molarity. So it's the formula of each compound raised to whatever their coefficient is. In addition, it's products on top, reactants on bottom, just as written how it is. if you plug in, so if you have a balanced chemical equation, you can actually generate the equilibrium constant expression. And the value, once you plug in those equilibrium concentrations, that will spit out the equilibrium constant. And again, the sub C means that concentrations are in molarity. Before these 3 chapters are done, you will see quite a few subscripts in there, each indicating a variation on the same idea. So again, in general, the numerator, the top number, is the product of the concentrations of the products raised their coefficient. Notice it's the product of the concentrations, meaning you multiply, not add. And the denominator, the bottom number, is the reactants raised to their coefficient. And once we know the balanced equation, we can write the equilibrium constant expression, because it depends only on stoichiometry, not mechanism. Kinetics does not really come into play when we start talking equilibrium. Now, one thing I want to stress is the value of that equilibrium constant at a given temperature does not depend on the concentrations of the reactants and products. The equilibrium constant for a reaction at a temperature is constant, which then does imply that changing temperature does change the equilibrium constant. It doesn't matter if there's any other substances present as long as they don't react with what we have. And so again, the constant only depends on the reaction and the temperature. So we're going to practice doing some equilibrium constant expressions. So I have 3 reactions here. We're going to write the equilibrium constant expression for. So that first one, it's always going to be a ratio, so I can kind of start with that. I see oxygen there as a product, so that's going to go up top. So in brackets, I do O2. And it has a coefficient of 3, so we're going to raise it to the 3rd power. On the bottom, the reactants, I see ozone. And it has a coefficient of 2, so 2. Let's look at this. So I see NaCl, so in brackets, NaCl. I apologize, I'm writing with a mouse. I see it has a coefficient of 2, so it gets a power of 2. On the bottom, I see 2 things. I see NO. Coefficient of 2 means the power of 2. And then we're going to multiply that by the chlorine. And it doesn't get any power because it has a coefficient of 1. And finally, that bottom one, give myself a nice big space there. So I get Ag NH3. Why did I do this to myself, I ask? 2, and then it has a coefficient of 1, so that's fine there. And then a G, trust me, that's a G, that's the best we're going to get. Sorry about that. It has no coefficient, so just a 1 times NH3. This one does have a coefficient, so a 2. Very simple, very straightforward, probably one of the easiest things with this entire section. Equilibrium constants in units. This is a little controversial. Your college professor may tell you otherwise, but the official party line from the AP board is they do not have units. They're a ratio, no units, just a number, leave it at that. Now, what is the significance of the equilibrium constant? This is the key part. Equilibrium constants can vary from very, very large to very, very small, or just mediocre. They're all over the place. So to analyze what the constant is telling us, we have to look at where it comes from. So again, given our general equation of products on top, reactants on bottom, if we have a very large equilibrium constant, that means the top number has to be much larger than the bottom. That means at equilibrium, we're going to have a lot of products and only a very small amount of reactants. And so we would say in that situation that the equilibrium lies to the right or favors the products, or we're going to have a lot of product at equilibrium. So here's just an example. So we have hydrogen, we have bromine, we're making HBr. We see the equation up top. On the left, we have a picture. We can see at equilibrium, we only have one molecule of Br2, one molecule of H2, and lots of HBr. So we would expect this top to be much bigger. So we would expect it to be a large number, or we say the equilibrium favors the formation of the products. But if the equilibrium constant is very small, that means the bottom number has to be very big. And when I say small, I mean it's between 1 and 0. We're never going to have a negative because you can't have negative concentrations. If at equilibrium we have much more reactants than products, we say the reaction lies to the left or favors the reactants. So once again, if the equilibrium constant is greater than 1, it lies to the right, favors the products. If it's less than 1, it lies to the left. We favor mostly reactants. And again, this is another example. So here we see nitrogen, oxygen making NO. At equilibrium, we only have a very small amount of NO compared to lots of the other things. So we should expect that to be less than 1. So an example, reaction of nitrogen to oxygen to form NO is considered a means of fixing nitrogen. Here's the reaction. There's the equilibrium constant. So is this a feasible method of fixing nitrogen by forming NO at this temperature? Well, if we look at that constant, this is way less than 1, which means at equilibrium, we're going to have very small amount of product of NO, which means this is not a feasible means of fixing nitrogen, of making NO at 25 degrees Celsius. So the direction of the chemical reaction in K. Because we can approach equilibrium from either direction, either looking at reactants to form products or from products to form reactants, the way we write a chemical equation is arbitrary. The way I do it is just take it as written. Take it as written. And if the whatever's to the left of the arrow is your reactants. Whatever's to the right is your products. So for instance, here is an equilibrium. So we have a number. We see products on top, reactants on bottom. We could also write it like this. It's the same reaction but reversed. Because again, at equilibrium, both reactions forward and reverse are happening. And if I do that, we get a different number. And you go, but wait, that's a different number. Well, yeah. Because with this top one, because that's less than 1, that means we favor the formation of the reactants, or N2O4. Written like this, we get this as our answer, which is more than 1, which means we favor products, which would be the N2O4. So again, we're still favoring the same thing. We've just swapped up who's the reactants and who's the products. And this gives us one of our rules. We can manipulate an equation. So if we're given an equilibrium constant for a given reaction, if we reverse the reaction, it's just the reciprocal of the equilibrium constant. So again, if we know the equilibrium constant for one reaction, for the reverse reaction, it's just the reciprocal of that value. So again, here's a reaction. So we have this. We have the equilibrium constant for the reverse reaction. The N2 plus O2 makes 2NO. We saw that earlier. So we're going to find the equilibrium constant for our target one. Well, if I notice, the target one is just the reverse of what we have. So I just have to take the reciprocal of 1 times 10 to the negative 30th, and I get 1 times 10 to the 30th. Pretty straightforward. Now, we can manipulate the chemical equation to give us new equilibrium constants as well. And the AP people love to ask this, especially in multiple choice. So just like the equilibrium constants of forward and reverse reactions are reciprocals, the equilibrium constant for related reactions will also be related in some way. In other words, if we mess with an equation, we can figure out what the new equilibrium constant should be. So let's say this is our reaction. And let's say this is our new one. So what's the relationship? Well, if I look at it, I can see that the new equation is twice what the original one is. I multiplied all the coefficients by 2. This would be the equilibrium constant expression. Should be pretty straightforward, just with the coefficients. And if you notice, that's the square of what was originally there. So the rule is whatever multiplier you multiply all the coefficients by, that becomes the power to the equilibrium constant. So because in this case, I doubled times 2 the coefficients, I take the constant, and instead of doubling it, I square it. If I tripled it, let's say I tripled it so that instead of a 2, that was a 3. Instead of a 4, that was a 6. So if I take the reaction and I multiply it by 3, that means I take the equilibrium constant and I raise it to 3. Now we can also add equations together, just like we did with the reaction mechanisms. So again, if they have multiple steps, we can use equations made up of 2 or more steps. And again, we find the total equation by adding the individual equations, canceling out identical terms on either side. So here's an example. So we have this, we have its equilibrium constant, we have this, we have its equilibrium constant expression. And now the overall equation is this, because you can see the BR2 got canceled, leaving us with everything else. So I'm adding the 2 equations together. So when I add the 2 equations together, it's the same as multiplying the equilibrium constant expressions. So if I added 2 equations, I just multiply their constants. So again, a summary, if I reverse an equation, I take the reciprocal of the constant. If I multiply the equation, that becomes the power that I raise the constant to. If I add equations together, I multiply their constant. So in 14.4, we're going to look at equilibrium situations when dealing with gases particularly. Luckily, that's pretty easy to do. We can actually use the partial pressure of individual gases in a mixture exactly the same way we've used concentration or molarity before. But instead of just a generic K sub C, we now replace it with K sub P. So when everything is gases, we can set up the equilibrium constant expression. Again, instead of molarity, we're using pressure, so we're going to have K sub P instead. And it'll look like this. Notice that instead of hard brackets, we're using parentheses and a capital P for pressure. The subscript will be the chemical. Everything is still raised to whatever their coefficient is, and it's still products over reactants. So fundamentally, it's exactly the same, just labeled a little bit differently. Generally, this is going to be in atmospheres. Doesn't have to be, though, as long as you're consistent. So you could be in torr, as long as everything is in torr. You just don't want to be mixing and matching your pressures. Now, we can convert between K sub P and K sub C, but we have to perform some algebra magic to do this. So magic, 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 magic. And there we go. That is our new equation. So K sub P equals K sub T times RT raised to the power of delta N. What are these variables, I hear you ask? Delta N is the change in the number of moles of gas in the equation. So it's product number of moles of gas based upon the coefficient minus reactant moles of gas based upon the coefficient. And then R, you would use 0.0821, assuming that everything is in atmospheres. So that's a pretty straightforward conversion. In 14.5, we're starting to look at what are called heterogeneous equilibria. So it's equilibria conditions where you have things in different states of matter. If everything's in the same phase, we call it a homogeneous equilibria. If everything's a gas, if everything's a solution. Heterogeneous is where we start mixing and matching. So the most common that you'll see is you'll have something be a solid where everything else is aqueous, or perhaps maybe something be a liquid where everything else is aqueous. Now, why do we have to deal with this? Why do we have to pay attention to this? Why is this a problem? So take a look at this reaction. So it's this lead 2 chloride, it's dissolving, it's now in water, so we have lead ions, we have chloride ions, If I try to write out the equilibrium constant expression for this, we run into a situation. What is the situation? We can't express the molarity of a solid. Remember, molarity is moles of solute per liters of solution. If something is a solid, not dissolved, that's aqueous, it doesn't have a molarity. So, how do we deal with this? How do we deal with the fact that we can't actually write out the concentration of this PbCl2? We ignore it. And that's actually all you do when dealing with solids and liquids. We just ignore solids and liquids. So the equilibrium constant expression for the above would simply be this. Notice that the solid would be on the bottom, so it's just there, or it's over 1, could put it. If we flip this around and the PbCl2 was the product, then we just replace that with a 1 on top. Now, as a note, even though the PbCl2 is not shown in the expression, it still must be present. When we are at equilibrium, there will still be PbCl2 present, but it just doesn't matter how much. And again, we can also ignore pure liquid. So we ignore water pretty frequently when doing equilibrium stuff. So again, that's what we see here. We see two situations. We have carbon monoxide, carbon dioxide, carbon. Doesn't matter how much solid carbon there is. It's all about the equilibrium at the, between the gases, or the equilibrium between the aqueous things. Now again, why can we ignore these? It's technically the concentration of a solid or pure liquid has a constant value. So if we double the mass of the solid, we double its volume. So its concentration stays the same. And we're all about change. And equilibrium constant expressions only have terms for things whose concentrations change. They're left out. So an example, we're going to write the equilibrium constant expressions for each of the following. So let's take a look at this. So that first one, so it's always products over reactants. So first product is that CO. I'm going to do this, we're K sub C, so we're doing brackets. So CO has a coefficient of 1, so no superscript listed. Water gets ignored because it's a liquid. Then on the bottom, I see, ooh, that was a terrible bracket. Again, I'm writing with a mouse. CO2 times H2. Everything has coefficients of 1. Everything gets raised to the power of 1. For the second one, same business. So this tin here, we get to ignore because it's a solid. So we simply go with CO2. It does have a coefficient, so we're going to label that a 2 right there in the superscript. In the reactants, I see the SNO2. Don't care about it. It's a solid. Only care about the CO. So CO. It has a coefficient of 2. So again, a 2. Now if you have a gas-style reaction, so this is what we see here. CaCO3 makes CaO plus CO2. One thing to notice, in this case, the K sub C is just going to be equal to the carbon dioxide concentration because everything else just cancels. Likewise, the K sub P is equal to the pressure of the CO2. And this is key. The AP people love to ask questions in situations like this. So the idea is if you have a gas like this, where the only thing in it is a single gas, the K sub P is its equilibrium pressure. Likewise, the K sub C is its equilibrium concentration. So at a certain given temperature, the equilibrium between calcium carbonate, calcium oxide, and carbon dioxide will always lead to the exact same value. Because again, same temperature, same equilibrium constant, and in this case, because the equilibrium constant is equal to the concentration or pressure, same constant pressure. And again, as long as all three are present. So let's take a look at a difficult example. So same reaction. So we have 4 different situations. And we're going to place each of these in a closed container, allow it to stand. We're going to ask, will it achieve equilibrium? So first off, if we put pure CaCO3 in, pure CaCO3. Well, I look at that and I go, okay, that's our only reactant. some of it will decompose, becoming CaO and CO2. So absolutely, it'll absolutely reach equilibrium. Ding. So now we have CaO and CO2, pressure greater than the value of K sub P. Now remember from the previous slide, at equilibrium, the pressure of the CO2 is going to be equal to the K sub P. Because it says the pressure is greater than the value of K sub P, that means the pressure of CO2 is too high. Since the pressure of the CO2 is too high, that means the pressure of the CO2 needs to decrease. Likewise, we have some CaO. So this can run backwards. The CO2 can react with the CaO. Those can react and form CaCO3. So yes, absolutely, we can reach equilibrium. So now we look at the third one. We have some CaCO3 and CO2 whose pressure is greater than the value of C sub P. So now we have CaCO3 and we have CO2 whose pressure is greater than the K sub P. So like the last one, that tells us that the CO2 is too much. It wants to decompose. Well, not decompose, it wants to react with the calcium oxide. But there is no calcium oxide. There's no calcium oxide for this reaction to run backwards. Why won't the CaCO3 just decompose, forming CaO and CO2? Well, that's because the CO2 pressure is too high already. Since the CO2 pressure is too high, the reaction's not going to run forward. Because there's no CaO for the reverse reaction, the reaction's not going to run backwards. So that one will not occur. And finally, we put in some CaCO3. We put in some CaO. Will it reach equilibrium? In this case, yes. We have our reactant, CaCO3. We have no CO2. Because we have no CO2, that means it needs to increase, and it can, because there's no CO2. So the CO2 pressure is less than K sub P. This will absolutely reach equilibrium. Okay, 14.6 is really where things start to escalate in difficulty a little bit. So we're going to be calculating equilibrium constants. The simplest way to calculate an equilibrium constant is when we know the concentration at equilibrium of each of the substances. For example, we're told at equilibrium we have these particular pressures, we have this reaction. So we're simply going to create the equilibrium constant expression, solve for K sub P. So here I have the equilibrium constant expression. I plug in all the values from above. And I get my equilibrium constant. Pretty straightforward. Unfortunately, most of the time we are not handed the equilibrium values themselves. We have to find them. But if we know the equilibrium concentration of at least one thing, we can use a modified version of stoichiometry to find the concentrations of all the rest. And then, once we've found the equilibrium concentrations of everything else, we can then solve for the equilibrium constant. To do this, we're going to use a tool called an ICE table, ICE. So we're going to tabulate all the initial and equilibrium concentrations that we know in the problem, hence I and E. I is for initial, E is for at equilibrium. We can then find the change in concentration. That's what C is, change. I initial, C change, E equilibrium. Now the trick of this is, and I want to stress this, in an ICE table, there's only two things that can go into an ICE table. First one is concentrations in molarity. The second is pressures. That's it. If you are given something that is not an equilibrium, or sorry, concentration or not a pressure, it cannot go in the ice table. So this is how this works. I'm going to show this with an example. We have a closed system. We know concentration of hydrogen. We know concentration of iodine reaches equilibrium. We find that at equilibrium, the concentration of HI is that. We're going to find K sub C for this reaction. That's our plan. So we know the initial concentration of hydrogen. We know the initial concentration of iodine. And we know at equilibrium, the concentration of HI is that. Now notice we are not told the initial concentration of HI. If in the problem we are not told that we are starting with an amount of a product, assume that it is 0. So we have our reaction, and we're going to set up our ice table, initial, change, equilibrium. So I'm going to walk through this. So I filled in for this first piece, for each chemical, the initial concentration as I knew it. Next, in the change column is all these X's. Generally, reactant concentration goes down, hence the negative. Reactant concentration goes down, product concentration goes up. Finally, the H2 is a single X, and the iodine is a single X because they both have a coefficient of 1. The HI has a coefficient of 2. That's why the HI has a 2x. So in the change, it's going to be plus or minus various x's. The x, 1x, 2x, 3x, 4x, is whatever the coefficient is from the balanced equation. And finally, we know the equilibrium concentration of HI, so I can put that right there. Now, if we know the initial and final of any of the substances, we can find its change. So we knew the change in HI, 1.87 times 10 negative third, that was the equilibrium, minus 0, the initial, gives us this. This is our change. Now we labeled it that the change is 2x. So 2x equals 1.87 times 10 to the negative third. Now we can know what x is, because we know that 2x is 1.87 times 10 negative third. That means x would be half of that, or 9.35 times 10 to the negative fourth, like we see there. So now we can simply subtract the change from the initial. So I do 1 times 10 negative third minus 9.35 times 10 negative fourth, and that gives me my equilibrium amounts. Now that I have my equilibrium amount, and this I want to stress, only things in the E row, in the equilibrium row, can go into an equilibrium constant expression. Again, in an equilibrium constant expression, it's all about things at equilibrium. So I plug in the numbers and I get my answer. It's a lot of work to get there, but it's consistent work. Now, just a quick question, does this reaction favor the reactants or products? Because 51 is greater than 1 last time I checked, that means this favors the products. So, another example. We have our reaction. We're told that initially the SO3 has a pressure of 0.5, and at equilibrium the SO3 has a pressure of 0.2. We're going to calculate K sub P. Done exactly the same way. So we're going to set up our ice table. So one thing I do like to do in these problems is I like to write the coefficients in the top. So I see that the SO3 has a coefficient of 2. I have my equilibrium arrow. The SO2 has a coefficient of 2. Oxygen would be a 1. So I put in my initial concentration of the SO3. Both of these here are 0 because we were not told any information about our product, so we assume that they are 0 in their initial. I am told that the equilibrium concentration of the SO3 is 0.2, so that's why that's there. And finally, we set up our change column. So again, the SO3 has a coefficient of 2, so 2x. SO2 is a 2, 2x. Oxygen is 1, x. So now we have enough information we can start processing this. This is everything we know. So we know that if 0.5 minus 2x equals 0.2, then at 2x will have to be equal to 0.300. And that means x would be 0.150. So I can actually put those in the equilibrium column. Now I have enough to actually solve this. So I set up my k sub p, plug in my values, and I get my answer. 14.7 is actually dealing with one of the most forgotten topics in equilibrium. It's called reaction quotient. So we know that if we look at the equilibrium constant K, it tells us in general how a reaction will proceed. In other words, how the relative ratio of reactant to product at equilibrium. Again, if K is large, we're going to have a lot of product at equilibrium. If K is small, a lot of reactant. But we can also use the formulation of the equilibrium constant to determine which direction will go based upon an initial condition mixture. All you have to do is find the concentration of the reactants and products really that we have. So we know which direction of the reaction is favored. That's based upon K. But let's say we have a mixture of reactants and products. So we want to know, how will the reaction change? Will we have to make more products to reach equilibrium? Will we have to make more reactants to reach equilibrium? That's where reaction quotient comes into play. Reaction quotient is capital Q. It is found the exact same way as K is, except you use initial values, not equilibrium values. So, to then find out what happens, you compare your Q value to your K value. If Q equals K, you're at equilibrium. If Q is greater than K, think of it this way. If Q is greater than K, that means your top number, your Q is too big. That means your top number is too big. That means your products are too much. So you have too much products, so the reaction is going to move from right to left, meaning you're going to make more reactants. Likewise, if your Q is less than K, that means your Q is too small. That means your bottom number, your reactants, are too big. So you're going to make more products. You're going to use up reactants, make more products. Here's an example. So we have a certain reaction at 448. Equilibrium constant is 50.5. Here's the reaction. We're given different molarity, different moles and liters of the components. So we're going to find the molarity first just by dividing the moles by liters, which is how we get that. Then we're going to plug into the exact same thing that we would do with an equilibrium constant expression, except we're using Q instead of K. Set it up exactly the same way. Products on top, reactants on bottom, everything raised to their coefficients. I plug in the numbers and I get my answer. So Q is 1.3. K is 50.5. Q is less than K. Q is too small. To make it bigger, that means the top number has to get bigger. We need to make more products. So that's what's. So we're now going to look at section 14.8. So this is flipping things around from the last section. The last section was solving for the equilibrium constant. Well, it turns out if we know the equilibrium constant, we can actually find the amounts of our reactants and products at equilibrium. So we can go either way. Again, we're either going to solve for the equilibrium constant, or we're going to solve for the amounts at equilibrium if we have the equilibrium constant. We're going to do this in a very similar way. We're going to use an ice table. Basically, get in the habit, if it's equilibrium, it's ice. The problem might not always need ice, but it's never a bad path. So here's a first example. We have the K sub P for reaction. There's the reaction. We're told at equilibrium, the partial pressure of hydrogen is 0.928, nitrogen is 0.432. We're going to ask for the partial pressure of NH3. So I set up my ice table. So we don't know the beginning nitrogen, we don't know the beginning hydrogen, But we do know the beginning ammonia is 0 because it's a product and we were not told an initial amount. Therefore, we assume 0. We know at equilibrium, we don't know. We're going to call this X because it's an unknown. So now I can jump to my equilibrium constant expression. We know K sub P is 1.45 times 10 negative fifth. We know the pressure of the ammonia is X, but then it's squared, so X squared because it's our unknown. Pressure of the nitrogen, pressure of the hydrogen. Notice we had to cube it because of the 3 there, because of its coefficient. And then we just rearrange to solve for X. I solve for X, and I get my equilibrium pressure. Pretty straightforward, just a bunch of algebra. Now, unfortunately, it's very rare to know all but one of the equilibrium amounts. Chances are we know the equilibrium constant because we can look that up, and we know the initial amount of everything because that's what we added. Then we have to solve for the amounts at equilibrium, and that's what we're going to see how to deal with. Luckily, we deal with this with ice. So we have a 1 liter flask, 1 mole of hydrogen, 2 moles of iodine. K sub C is given. There's the reaction. The problem could have been nice and just given us molarity, but it's in 1 liter, so molarity is easy to get. And we want to know what are the equilibrium concentrations of hydrogen, iodine, and hydrogen monoiodide. Okay, that's what we're looking for. There's equilibrium. I'm going to use an ice table. So I set up my ice table. I can see I have everything set up. Initial concentration. We were not told an initial amount of HI, so it's a 0. Initial setup. Now we're going to use stoichiometry for the change. So again, hydrogen, because it has a coefficient of 1, goes down by X. Iodine with a coefficient of 1 goes down by X. Again, they're going down because they're reactants. And hydrogen monoiodide, because it had a coefficient of 2, and it's a product, goes up by 2x. So we know the change. The equilibrium is now just putting these together. So the equilibrium is 1 minus x for the hydrogen. 1 minus x, that's what we get there. 2 minus x. 0 plus 2x is 2x. Now, it's just algebra. Well, it's a lot of ugly algebra. So we're going to substitute those equilibrium amounts into the equilibrium constant expression. So I have my equilibrium constant expression. I already had the K sub C given to us. And I plug everything in. Notice, like here, so the 2x is because HI had a coefficient of 2. Because it has a coefficient of 2, it's also the superscript. It feels wrong to do that to some people. It feels like you're double dipping that coefficient. And you are, but you're supposed to. So we plug everything in, and now we use a bunch of algebra. If you have a fancy calculator, make your fancy calculator do this. If you don't have a fancy calculator, you've got a quadratic equation on your hands. So in this case, I multiplied 1 minus x times 2 minus x. That gives me this mess here. I then multiplied both sides by that mess, so that's where we get the 50 times that. I expanded the 2x squared is 4x squared. I distribute, I set for 0, I use the quadratic equation, and I get 2 answers. Now we have to choose which of those 2 answers. Substitute them in to the equilibrium amounts to see if it makes sense. So we know that if we start with the 2.323 as x, remember hydrogen is 1 minus x. Well, if x is 2.323, we'd end up with a negative concentration. You cannot have a negative concentration, therefore it has to be the 0.935. So I subtract, I get the hydrogen ion concentration, I get the iodine concentration, and I get the HI concentration. So again, anytime you do the quadratic, you're going to get two answers. You're going to have to choose which to use. Okay, we're in our last section of the chapter. We're looking at 14.9, Le Chatelier's principle, or Le Chatelier. Yeah, don't do that. Anyway, Le Chatelier's principle is a very conceptual chunk of equilibrium, very important. So it's officially stated as, if a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. That's a lot of words not saying much. This is what it means. If we mess with the reaction at equilibrium, the system will change to accommodate what we've done. And the heart of this is the equilibrium constant. We know that at equilibrium, at a certain temperature, there is a set ratio of reactants to products in terms of concentration. If we start messing with that, that actually changes the distribution of reactants and products to go back to that constant. Changing the temperature actually shifts the constant itself, which will then shift the distribution of the reactants and products. And that's what this is about. So we're going to start with changing the reactant or product amounts. So if a reaction is in equilibrium, and we add something, either a reactant or a product, the reaction will shift to reestablish equilibrium by consuming part of what was added. Think of it as we were at equilibrium, we were at the ideal ratio, then we mess it up. We add something. System now goes, uh-oh, too much of that thing. It's going to get rid of that thing by making the other. In other words, if I add a reactant, it goes, uh-oh, too much reactant, need to use it up to make more product, to reestablish that ratio. Vice versa with the product. If we add product, system goes, uh-oh, too much product, gotta use it up. We use it up by making more reactant. So here's just an example. So we have this equilibrium between N2O4 and NO2. And we can see that we were at equilibrium. We're going to add more NO2. NO2 is a product. So what happens is, because we now have too much product, too much NO2, NO2 is going to get used up to make more N2O4. We say the system shifts to the left. That just means we're making more reactant. That just reestablishes that same ratio we had before. So consider this. So what would happen if I added more nitrogen? Well, if I added more nitrogen, we now have too much reactant. We get rid of reactant by making more product. So it's going to shift the equilibrium to the right, forming more ammonia, also using up more hydrogen. So when equilibrium is reestablished, hydrogen amount actually went down, but the ammonia went up. What happens if we add more hydrogen? Same idea. The system goes, oh, too much reactant, got to get rid of it. Gets rid of it by making more product, makes more NH3. But nitrogen now gets used up. What happens if we add more ammonia? System goes, uh-oh, too much product, got to get less. It decomposes the ammonia back into the reactants, so the nitrogen and the hydrogen amounts increase, again, to reestablish that same ratio. Now, here's a removing. If I remove ammonia, same logic. System goes, uh-oh, now not enough product, need to make more. It makes more product by using up reactant. So it'll shift to the right, forming more ammonia, using up nitrogen and hydrogen. So now look at the effect of volume and pressure change. So if we change the volume, let's say we decrease the volume, which increases the pressure, the system will shift to reduce the pressure. Same idea. We increase the pressure, it's decreasing. Notice we're doing this through a volume change. Now, the way that this happens to reduce the pressure, because we increased it by decreasing the volume, is we're going to reduce the pressure by reducing the total number of gas molecules. Again, more molecules, more pressure. So lowering the volume, which increases the pressure, causes the system to shift in the direction that reduces the number of moles of gas. And this is purely in terms of coefficients, stoichiometric coefficients of gases. So here's our example. We have N2O4 on the left with a coefficient of 1. We have NO2 with a coefficient of 2 on the right. They're both gases, so that's all we care about. If I decrease the volume, which increases the pressure, system now goes, uh-oh, too much pressure. It's going to reduce it to the side with fewer moles of gas, which would be the reactants. So the reaction would shift towards the reactants. So when equilibrium reestablishes, we're going to have more N2O4 than we had and less NO2 than we had. And we can see this, sorry about that, see the same thing here. So if we increase pressure on this reaction here, increase pressure by decreasing volume, because we've increased the pressure, that means the amount of moles needs to decrease. I look at my sides. Left side has 4 moles of gas, right side has 2, so it's going to shift to the right. Likewise, if I increase the volume, which decreases the pressure, it's going to shift to the side with more moles of gas. So same reaction. So again, there's 4 reactant molecules to every 2 product molecules. So again, if I increase the pressure by decreasing the volume, it's going to shift the equilibrium to the side with fewer gas molecules to the right. If I decrease the pressure, it's going to go, need more. It's going to make more by shifting the side with more molecules. Now, just as a reminder, pressure volume changes do not change K. As long as temperature stays the same, K remains the same. All we're doing is shifting partial pressures. So here's another way to look at this through the reaction quotient. Same reaction, here's the K, and we're saying this is the amounts that we have at equilibrium. That's what we're provided. Now, if I reduce the volume by half, if I did not shift the equilibrium, then the partial pressure of each would double. Half the volume, twice the pressure of each. So that would give us these amounts, these pressures for each. And if I plug those in to our equilibrium constant expression for Q, because we're no longer at equilibrium, we get a vastly different number. This Q is far less than our K. And remember, if Q is less than K, that means it's too small. That means we need to make it bigger. We need to have a bigger top number. We need more product. So we're going to have to make more product. So shifts it to the right. Now, what happens if we have a pressure change without the volume change? So let's say if we add a chemical, so for here, if additional amounts of any of the reacting components are added or removed, if we add a gas not involved. Now, as a note, so with the first one, if I add or remove anything that's part of the reaction, then it's simply just a adding or removing stuff problem. Now, if I add something that's not involved, that changes nothing. So if I have a reaction and we pump, let's say, the container full of argon, and argon's not involved in the reaction, no change. Didn't change the partial pressure of any of the others, doesn't change anything. Finally, we're going to look at temperature change. Basically, if temperature changes, equilibrium constant changes. But the temperature dependence, we look at it through the lens of Le Chatelier's principle. We're going to treat heat as if it's a chemical. It's not, but we're pretending that it is. If it's endothermic, we're going to treat heat as a reactant. If it's exothermic, we're going to treat heat as a product. Then when we change the temperature, it's like we're adding or removing the heat. So if it's endothermic and we increase the temperature, it's like adding a reactant. If we increase the temperature and it's exothermic, then it's like adding a product. And then the equilibrium will shift to consume that, just like we would with adding or removing a chemical. So if I add heat, it's going to go, oh, too much of wherever the heat is, we need to get rid of it, shifts it to the other side. Lowering the temperature is like taking something away. It's going to make more of that side. So here's just an example. So we see this equilibrium situation between N2O4 and NO2. N2O4 is colorless, NO2 is brown. Because the heat is here in the reactants, that means it's endothermic. If I lower the temperature, that's like taking heat away. So if I lower the temperature, it takes heat away. If I take heat away, it shifts the equilibrium to the left and it becomes colorless. But if I raise the temperature, like we are here, that's like increasing the amount of heat. So to balance out increasing the heat, it's going to try to make less of it, shifts it to the right, and it makes it brown. So again, what this means, if it's endothermic, increasing temperature results in increasing K, because increasing temperature means we're going to make more product. More product at equilibrium means higher K. Exothermic is the opposite. If it's exothermic, increasing T actually drops K. And cooling is just the opposite of heating. So here's an example. Here's an equilibrium. So we look at that number. Because it's positive, that means it is endothermic. Endothermic. So if I add N2O4, because that's a reactant, we're adding a reactant, that should shift our equilibrium to the right. If I remove NO2, I just removed a product, so it needs to make more, so it would shift it to the right. Same reaction. Let's say I increase the total pressure by adding nitrogen gas. Well, nitrogen gas isn't part of the reaction, therefore no shift at all. What if I increase the volumes? This one's tricky. If I increase the volume, that decreases the pressure. By decreasing the pressure, it's going to shift things to the side with more moles of gas because it's going to want to bring it back up. The right has more moles of gas, so it shifts it to the right. Finally, temperature is decreased. Again, this is endothermic because that is a positive delta H, which means heat is a reactant. So if I decrease the temperature, it's like removing heat. It's like removing a reactant. So it's going to shift it to the left to make more reactants. Finally, catalysts. Remember, catalysts lower the activation energy of everything. So it lowers, well, the activation energy of everything. So it does not change equilibrium at all. No shift.